Hi, hello everybody. Welcome back to IIT Academy. And today we are going to discuss about the next periodic property, which is ionization energy. Ionization energy is also called as ionization enthalpy. So let's start. The definitions, the formulae are very, very easy. But then while practicing the questions, we'll understand how concepts are actually meant to be applied. Okay, so please do not take any topic lightly. You might have, gone through these definitions. You might have heard of these titles long back from your school days, but please do not take it lightly because you will understand the depth and the extent to which you make mistakes when you actually do problems. Okay, so let's start. Ionization energy, very easy. Let's say you have any species from an isolated, or let's write the definition first. That's the amount of energy required to remove an electron from an isolated gaseous atom is ionization enthalpy or energy. I'm going to represent it as IE throughout the session. Okay, so very important, ionization energy by default is defined as the energy which is required to remove an electron. But it is important to note that it should be from an isolated gaseous atom, which is in the gaseous state. Okay, that is how it is actually defined. Now, ionization energy can have various units, okay? In questions, you can get it in electron volts, or it might be represented in joules per mole, or in certain cases, it can be in kilojoules per mole. All these are possible values of ionization energy, as it is the energy which is required to pull one of the electron from the atom. Correct? So let's say that you have a nucleus and there is one electron which is very near to the nucleus, and there is another atom, okay? And from this atom, you have to remove an electron from here. So I hope you're getting the scenario. Always the ionization energy is defined as the energy which is required to remove the outermost electron. So let's say this is the outermost electron in the first case A, and here there are other electrons inside. But then because of the size of the atom, this is the outermost electron. Now just imagine the case. So here the electron is in close proximity with that of the nucleus, and this electron will feel the positive charge of the nucleus. Positive charge of the nucleus is also known as effective nuclear charge, right? Will feel the effective nuclear charge beautifully and is bound tightly. While over here, this electron is very far away from the nucleus, and there is a lot of screening or shielding happening over here, and hence this is loosely bound in case B. So what I can say is the energy which is required to remove the electron from A is definitely going to be higher than the energy which is required to remove the electron from B. Correct? So the higher the value of the ionization energy, greater the difficulty it is. Right? Greater the value of ionization energy, it means it is more harder. It means it is harder to remove the electron from the species. Always remember, electron which will be removed will of course be the outermost electron. Correct? Because that would be the least, the one which is feeling the least effective nuclear charge. Remove the electron. Correct? So you have to give some amount of energy. You have to give some amount of energy. So based on which you will get questions of first ionization energy, second ionization energy, third ionization energy. What does that mean? let's say that you have got some metal and you have taken its isolated gaseous state. And from this, if you remove one electron, so one electron, negative charge is removed, the metal will now carry a positive charge plus one electron. So you have removed one electron, and this corresponds to the first ionization energy. I'm writing it as IE1, 1 as the subscript. Okay. Next, let's say from this M plus, I'm again removing one more electron to give M2 plus. Then what is this? So here, if you compare M to M2 plus, two electrons have been lost. Correct? So from M to M2 plus, two electrons have been lost, which means it is the second ionization energy of M, or this can be written as the first ionization energy of M plus. Correct? This was M plus. And from here, you're removing only one electron. So it can be written as the first ionization energy of M plus or the second ionization energy of M. Correct? Similarly, I can write, let me write once again, one more step. Let's say M2 plus. Again, I remove one electron from the outermost shell. And now this can be written as the third ionization energy of M, or the second ionization energy of M plus, or third ionization energy, or the first ionization energy of M plus 2. Correct, it's very easy. So this is how you can get questions. You can get questions either from the first ionization energy or the second or the third. So you have to be very careful on how they are asking the questions. Now, there is a particular order in which you have to check the order of ionization energy. Okay, so you write order of factors affecting the ionization energy on adjacent atoms. Very important. Students make mistakes over here. So what I'm going to tell is the order or the priority, the order in which you have to look at the factors that decides the ionization energy, and this can be applied only on adjacent atoms. For example, these order that we are going to write can be applied on nitrogen and oxygen because they are adjacent to each other. Correct. But they cannot be applied on nitrogen and fluorine. Why? Because they are far apart. Okay. So whatever sequence of priorities or whatever sequence of factors that I'm going to mention can be applied only if the atoms are adjacent to each other. Adjacent to each other. Okay. So the first one is noble gas configuration. You know what noble gas configuration is by now? That means the complete shell will be filled with electrons. Correct? Helium, neon, argon, krypton, xenon, radon, these are all noble gas configuration. So if it is complete, that means it is satisfying the octet or it is satisfying the doublet. So noble gas configuration will have very high ionization energy. That is for sure. So this is the first priority which is given. Okay. Second is penetration power. Ionization energy is directly proportional to the penetration power. Now, what does penetration power mean? It varies with the subshell. The penetration power of S is larger than P, then D, then F. Okay. So if you have two adjacent atoms where you have atom A where the last electron enters into S, and you have atom B where the last electron enters into P. What will you check? You will check the penetration power. The penetration power means if it is in S, the ionization energy will be high. If it is in P, the ionization energy will be small. Why? Because if you consider this as the nucleus, S is the closest. Correct? S is the closest, so it will be tightly bound. So the energy which is required to remove an electron from S subshell will be high because it will be the closest to the nucleus. That is called the penetration power. Okay. Third one is half-filled configuration. Electronic configuration. So you know electronic configuration like P3, which is half-filled, D5, F7, these are all stable. Why? Because these are half-filled configurations and they give high exchange energy, about which we have already discussed. So such configurations will also be favoring. Not only half-filled configurations, fully filled configurations also. They have very high exchange energies and hence are stable. Right. Now the last one is Z effective. Higher the Z effective, closer it will be bound to the nucleus and it is more difficult to remove the electron. So this is the order in which you have to check the order of ionization energy for, again and again I repeat, for adjacent atoms. For adjacent atoms. Okay? Let's do a few examples so that you can understand. Okay. So the first question is, let's say, I am removing an electron from Fe plus 2. It is becoming Fe plus 3 plus electron. So this is one electron is removed from Fe plus 2 and the ionization energy is, let's say, X. Okay. Now, similarly, I'm removing from Mn plus 2, becoming Mn plus 3 plus electron, and the ionization energy over here is Y. You have to compare X and Y. So to compare X and Y, the first thing that we can check is to write the electronic configuration. So let's write the electronic configuration. Fe plus 2, Z is 26 of iron. 2 electrons are lost. So what it will become? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Just a minute, let me check if it is recording. Okay, so this is that of iron. Now, if we have to remove 2 electrons, we know that the Z effective on 4s is less than that of 3d, and hence the electrons will be lost from 4s. So this is the configuration. Okay, this is the configuration. So you're removing 1 electron from 3d6 to get Fe plus 3. Now, in the case of Mn2 plus, whose Z is 25, Mn is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. So we need Mn plus 2 electrons will be removed from S. This is how it is. Now to become Mn3 plus, you have to remove 1 electron from 3d5 to make it Mn plus 3. So you know d5 is a half-filled configuration. So if it is a half-filled configuration, of course, its ionization energy will be high. Correct? So if you check the order, these are not noble gas configurations. Criteria 1 gone. Criteria 2 is penetration power. Both of these belongs to D. So that is also gone. So third one is configuration. So if you check the configuration, this is half-filled. So the ionization energy of Mn plus 2 is going to be way higher than the ionization energy of Fe plus 2. Okay, meaning Y is greater than X. This is how you do it. Okay, next question. Let's say you have to come Na plus, who's becoming Na plus 2 plus electron. Ionization energy is X. And neon, Ne plus, plus electron, ionization energy is Y. Okay. So here, as I said, the first thing that we'll be checking is noble gas configuration. So for Na plus, what is the configuration? Na is Z is equal to 11. 1s2, 2s2, 2p6, 3s1. This is sodium. So sodium plus means this is gone. Okay. Next is neon, which is 10. 1s2, 2s2, 2p6. So you can see that both of them have got noble gas configuration. Both of them are ending in P subshell. So the penetration power is also the same. Configurations are also the same. So the next one is effective nuclear charge. You can see that here sodium is already positive. Correct? Already one electron is lost. And then you have to remove another electron, which is way tougher. It's tough because already one electron is lost. So you know that the parent cation, so the cations we have already learned are smaller in size than the parent species. Correct? So if they're smaller in size means they'll be closer to the nucleus. If they're closer to the nucleus, it is even harder to remove the electron from Na plus. While this one is neutral. So ionization energy of Na plus is going to be greater than Na. Okay? Got it? Okay, let's do one last question. And then we'll go to the application part. Let's say you have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay. You have to write the order of ionization level. Or let's say you have to write the order. Okay. Let's write the order of second ionization. So what will happen? This will become plus, 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 and plus. So one electron is lost. You have to write the order of second ionization energy. So first of all, let's write the configuration of all the species. This is atomic number 3, 4, 5, 6, 7, 8, 9, 10. Right. So 3 means one electron is lost. This is 1s2. Beryllium will be 1s2, 2s1 because one electron is lost. Boron is 1s2, 2s2. Carbon is 1s2, 2s2, 2p2 actually, but one electron is lost. Here 1s2, 2s2, 2p2. Here 1s2, 2s2, 2p. How many? 8. One electron is lost, so it is 7, 3. 1s2, 2s2, 2p4, and finally 1s2, 2s2, 2p5 is what you have. Okay, so let's check them one by one. Lithium and, let me change the color. Lithium and beryllium. So this is 1s2 noble gas configuration. This is 2s1. So from the criteria, we know that noble gas configuration will be given higher priority. So lithium plus is greater than beryllium plus. Okay. I'll write the answer over here. Lithium plus is greater than beryllium plus. Next is boron plus. If you compare beryllium and boron, we can see that this is 2s1 and this is 2s2. 2s2 means it is fully filled and this is half filled. So of course, fully filled will be given more priority than half filled. So this is like this. Now coming to carbon. Carbon again is this is S2 fully filled. This is only P1, which is just one occupied. Or in terms of penetration power, this is S and this is P. S has got more penetration power and hence more ionization energy. All right. You're getting it right. Now, next one is P1 and P2. No noble gas configuration, comparable penetration energies. Configurations are also not half filled or full filled. So the next one will be effective nuclear charge. So as we know, from left to right, effective nuclear charge increases. So if effective nuclear charge increases, it will be bound more closely to the nucleus and hence difficult to remove the electron. So N plus. Next is with oxygen. Oxygen C, oxygen plus is half filled. This is only 2p2. So O plus. Correct. Next you have F plus. So you have P3 half filled configuration here and you have P4 over here. Half filled configuration will of course get more priority. And last one is Ne plus. No noble gas configuration, penetrations are the same. Configurations are not half or full. So next what you'll be checking is Z effective. Z effective, as you move from left to right, your Z effective increases. So if your Z effective increases, your ionization energy also increases. Periodic property. Right. So this is again like this. So this is the order for the adjacent species. So we have taken adjacent species into consideration. We have taken adjacent species into the consideration. Okay. Now let's say that you have to write the actual order in a continuous decreasing or increasing order. So what will you do? What you have to consider over here is, see, this one is noble. Lithium plus is noble. So definitely noble gas configuration, that will come first. Lithium plus. And then if you check, lithium, beryllium is small, but then boron is higher. So you might think that next boron plus will come, but no, it's not like that. Why? Because throughout the period, Z effective becomes dominant across the elements, not adjacent. If you compare lithium plus and Ne plus, what happens is Ne plus, because it has a very high Z effective, this comes next, not B plus. Okay, then you have to write the order from the right because Z effective dominates. So check, as you move from left to right, the Z effective dominates, correct? So lithium, and then highest comes neon. Fluorine is less, but fluorine, in comparison to fluorine, oxygen has got higher value. So oxygen plus comes next. Okay, that's it. And then you have F plus. Then next one is N plus. Next one is carbon and boron. If you compare, boron has got higher value. So boron, carbon, and beryllium. This is the final order. I do understand that this might find a bit tricky. This is based on the experimental values, but this is just to make you understand that all the priorities that we have written can be compared only between adjacent species, and not across. Okay, so this is the order. I don't think so you will get such long questions. We'll do some questions based on which questions are asked. Okay. Okay, so one more thing is stability of the states. Stability of the states. What it says is there are three cases. One is if the ionization energy of N plus 1 minus the ionization energy of N, and you take the modulus of this, is greater than 17 electron volts. Okay? If it is greater than 17 electron volts, it means lower oxidation state is stable. Okay. For example, you have certain metal who undergoes the first ionization energy to give M plus electron, and this is the first ionization energy, IE1. Okay. Now this further undergoes ionization, and this can be called IE2. Correct? IE2 of N. Correct, na? So this is IE1 of N. So you have got two products. One is M plus and the other one is M2 plus. Two products after ionization. If you have to check which one is stable, is it M plus or M2 plus? What you will do is, you will take the modulus of IE2 minus IE1. And if this is, let's say, greater than 17 electron volt, you will say that among the products, the one which is in lower oxidation state, M plus, is more stable. M plus is more stable. Okay. Second case, if IEN plus 1 minus IEN is less than 11 volts, electron volts, then higher oxidation state will be stable. Higher oxidation state is stable. For example, let's take the same scenario. And in this scenario, what I get over here, upon subtracting IE2 minus IE1, and when I take the modulus, if I get a value which is less than 11 electron volts, then among the two oxidation states, the one which is higher, which means M2 plus, is stable. Okay. Very easy. Now, third case is between IEN plus 1 minus IEN. You take the modulus and whose value is in between 11 to 17 electron volt means the atom exists in variable oxidation state. Exists in variable oxidation state. That's all. Okay. Like manganese plus, 2 plus, 3 plus, so on and so forth. Can go up to Mn plus 7. Right. Okay. So I hope you understand how this can be done. Very easy. Okay, now based on whatever we have learned, before giving you assignment, let's do some practice question in the class itself. Okay. First question, which equation best represents the first ionization energy of magnesium? So we said ionization energy always means that whatever species that you're taking should be in the gaseous state. Okay, so over here it is solid state, so this is wrong. Here also solid, wrong. Here also solid, wrong. So this one, option C is the correct answer. Option C is the correct answer. Why? Because you have a gaseous state of species from which one electron is removed. So ionization energy is defined as the energy required to remove an electron from isolated gaseous atom. Isolated gaseous atom. Okay. Second question. Which of the following transition involves the maximum amount of energy? So we have already done a similar question of this type. Ne plus, Na plus and Ne. So here electron is lost from a species who is negatively charged. Here electron is lost from a species which is neutral. Here electron is lost from a species which is positive. And here it is lost from a species which is doubly positive. Which will be higher? Logic, common sense, D. Why? Because you have to remove an electron. And as your charge on the species increases, the size reduces. Correct? As positive charge increases, the size reduces. As size reduces, the Z effective increases. As Z effective increases, your ionization energy also increases. Correct. Oh, third question. Which of the following electronic configurations of atom has the highest ionization energy? We already know what is to be done. We know the priority, right? Let's check the priority. This is half filled. Uh, we'll first check for noble gas configurations. Are there any noble gas configurations? This is half filled. This is 3s1. This is a noble gas configuration, correct? 6 plus 4, 10. Z is equal to 10. That corresponds to neon. It's a noble gas. So, noble gas configuration will get the highest priority. C is the correct answer. Question number 4, a very good question. The first 5 ionization energies of an element are 9.1, 16.2, 24.5, 35, and 205.7. The number of valence electrons. So if you can see over here, okay, observe. If you can see over here, we can understand that on moving from 9 to 16, the change is very small. Only 7 electron volt change. From 16 to 24 also, it is very negligible, 12 only. From 24 to 35, again very small, around 10.5. Now from 35 to 205, the jump is very huge. The jump is very huge, meaning a lot of energy has to be, just a second, please. Okay, sorry. A lot of energy has to be spent to remove an electron after this. Correct? So see, this is the energy which is required to remove the first electron. 9.1. This is for second, this is for third, this is for fourth, and this is for fifth. Right? The first ionization energy. So after 4, a lot of energy has to be spent for the electron to be removed. That is because it might have attained noble gas configuration, of course. Logically, that is what we think. So the number of valence electrons would be, answer is easy, 4. Because after 4, it will have noble gas configuration. So the number of valence electrons would be 4. Same question, similar question. First, second, and third ionization potential values of 100 are 100, 150, and 1500. Can you see? Here there is only, this is for the first electron, second electron, and third electron. So from 1 to 2, it's very easy. For the first electron, only 100. For the second electron, only 2. For the third electron, is 1500. There is a huge jump, 10 times. 10 times energy is required to remove the third one. So after the removal of 2, it might be again attaining noble gas configuration. So let's write the configuration of all of these species. Beryllium is 1s2, 2s2. This one is 1s2, 2s2, 2p1. This one would be 1s2, 2s2, 2p5. Sodium is 1s2, 2s2, 2p6, 3s1. Okay. So here, after 1 electron itself, you are getting noble gas configuration. But the change or the jump in the ionization energy is only observed after the second electron removal. So it's not sodium. Here, the 5 electrons should be lost or 1 electron should be added to attain. So it's not. Here also, after 1 electron, it is attaining noble gas configuration. But A, see, after 2 electrons, it is attaining 1s2. That means the third electron has to go from 1s2, meaning a high energy requirement would be there, and hence the correct answer is option A. A. Next question. Find the highest ratio of ionization potential for a given pair of elements. So if you check the elements, all of these are noble gases. Okay, so I'm writing the order of the noble gases. You have helium, neon, argon, krypton, xenon. This much is what you have in the options. And we know that as we move down the group, ionization energy decreases. Why? Because the size becomes larger and larger, the shells increase, so the energy which is required to remove the electron from the outermost shell becomes very easier. Okay, so in the first case, A, it is between helium and neon, adjacent. Second one, neon and argon, adjacent. Third one, C, helium and xenon, first and the fifth. D is krypton and xenon, adjacent. So of course, the ratio, helium has got the highest, xenon has got the lowest. Correct? So the ratio of the ionization potential will be highest for helium is to xenon. Option C. Option C. Okay. Now a few important questions. The order of ionization energy of nitrogen atom, nitrogen molecule, oxygen atom, and oxygen molecule are important. Important. So for this, actually, you should know the molecular orbital diagram. For the sake, I'm now giving it. I'm now giving it to you. Okay. So we know that nitrogen has got 7 electrons and N2 will have 14 electrons. So the way you fill these electrons, 14 electrons are, you have 1s of nitrogen, 2s of nitrogen, 2p of nitrogen. So these are two nitrogen N atoms and they combine to form N2. You will learn them. Okay, so for nitrogen, we already know that it is 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. We already know this, right? This is 1s, this is 2s, this is 2p of the atom. Now you have to fill these 14 electrons over here. Understand that this is sigma star, this is sigma. You might be familiar with this, sigma star. This is pi, sigma, pi star and sigma star. So you have to fill 14 electrons. So how will we fill? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is how you have. So if you check over here, let me zoom over here. So if you check over here, the last, we know that ionization energy is the energy required to remove the last electron. Okay, so if you check over here, the energy of the last electron in N2, molecular diagram N2, is lower than N, correct? So I can write that the ionization energy of N2, the energy which is required to remove the last electron from N2, which is in sigma, whose energy is lower than 2p, is less than N. I can write like this. Correct? I can write like this. Similarly, we'll draw for O2 as well. So for O2, 1s2, 2s2, 2p4 is what you have. So it becomes sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and here there is a slight change. It is 1, 2, 2, 1. This is how it is. You will learn why the order is different and all in chemical bonding. Just understand the concept now. Okay. So here you have 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. This is how you have it. Okay, we have to fill 16 electrons now. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now see, this is from the 2p of oxygen. Okay, so the energy which is required to remove the last electron from O2, whose position is higher than that of O. So the ionization energy to remove the last electron from O2 is lower than that of O. Listen over here very carefully. As let's say that this is the nucleus. This is the position of the nucleus. If this is the position of the nucleus, the farther you are, easier it is. I made a mistake. The farther you are, the easier it is. So here, nitrogen atom has got highest potential energy. I made a mistake. Please listen. The potential energy of nitrogen atom is higher than that of N2 molecule, means its position is very far away from that of the nucleus. It is easier to remove the electron from N from that of N2. The electrons of N2 who possess lower potential energy is closer to the nucleus and hence will possess higher ionization energy. So the order that we have written over here is potential energy. This is potential energy, not ionization energy. Okay. Similarly over here, O2, whose electrons are filled, are very far away from the nucleus than that of the 2p subshell of oxygen. So if they are far from the oxygen, it is easier to remove and hence O2 is less than O. Got it now? Now you got it. Okay. So now you know that N2 is highest than N and oxygen is highest than O2. On comparing nitrogen and oxygen, they are adjacent to each other. This is P3 and this is P4. Half-filled configuration will be more stable and hence it will have higher ionization energy. So this is the final ionization. Okay. I hope you get it. Again, I repeat, whatever order is written over here is the potential energy. So if potential energy is high means very far away from the nucleus and hence a very small amount of energy is required to remove an electron. Potential energy and ionization energy are inversely proportional. Oh. Similarly, next question, also important. Write the order of ionization energy for CH4, H2O, NH3 and HF. See, this is CH4, where all bonds are only sigma. But if you take the other species, here you have lone pair of electrons. In NH3, you have one lone pair of electrons. And in HF, you have 3 lone pairs of electrons. Okay. So, to remove an electron from the non-bonded electrons, species will be easier, of course. Because here they are bound, they are in a bond. Here they are non-bonding. Correct, they are non-bonding. So it is easier to pull an electron from here, which is not in a bond, than here. So CH4 will have the highest ionization energy. For sure, because it has no non-bonding. Now, among these three, you have to check the electronegativity. Okay. Electronegativity of fluorine is greater than that of nitrogen. No. Is greater than that of oxygen and then nitrogen. This is the order of electronegativity. That means Even if fluorine has 3 lone pair of electrons, it will pull the electrons very close to itself. It won't leave the electrons. So the ionization energy is very high. So after CH4, you have HF, then water, then NH3. Why is that? Water has got 2 lone pairs. That doesn't mean that it is ready to give the 2 lone pairs. No. As the electronegativity of oxygen is higher than that of nitrogen, it will keep the electrons closer to itself and not giving it. So the ionization energy of the oxygen containing water is higher than that of nitrogen. Okay? So here we compare the electronegativity of fluorine, oxygen and nitrogen. So can you see how questions are framed? It's not just from the definition. There are a lot of other concepts as well. So if question 8 is clear to you, please try question 9. You have PH3. Phosphorus has got a lone pair of electrons. You have got PF3. Here also phosphorus has got a lone pair of electrons. So during ionization, electrons will be lost from this lone pair of electrons. So who will be giving it easier? Of course, PH3. The ionization energy of PH3 will be less than PF3. Why? Because the electronegativity of fluorine is greater than that of H. So the electrons will be closely kept towards itself in PF3, not leaving the electrons, while in PH3, they are ready to be donated. Okay, the last one, tricky one. Pause the video, try it by yourself and then compare. Okay, so if we already know that the cation's ionization energy will be definitely higher than the parent species. So if you compare Zn plus and Zn, the ionization energy of Zn plus will be higher, right? And if you compare Cu plus and copper, the ionization energy of Cu plus will be higher. Why? Because here there are positive charges, which increases the Z effective, making it higher for the ionization energy to remove an electron. So now we understood that Cu plus is greater than Cu and Zn plus is greater than Zn. Now let's compare Zn and Cu. So if we compare Zn and Cu, Zn, how can we do that? Zn is of course fully filled. We can write the configuration. Let's try with the configuration. Zn is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Completely filled. While copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. We know this, right? So fully filled configuration will be given more priority than half filled. So S is half filled over here. S is fully filled over here. So Zn is greater than Cu. That also you got. Okay. So now we know that Zn plus is greater than zinc. Cu plus is greater than Cu. Zn is greater than Cu. Now the next challenge is between Zn plus and Cu plus. We have to compare that. So for Zn plus, the electron will go from here because the Z effective of 4s is the least. We have already done that from the Slater's rule. So this becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10, while Cu plus becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d10. Now this has become half filled and this has become fully filled because this is 0. So Cu plus is greater than Zn plus. Are you getting the point? So if we connect all of these together, copper plus is greater than zinc plus. Zinc plus is greater than zinc. And zinc is greater than copper. This is the order. A beautiful and important question. If not done properly, you will make mistakes. Okay. So yes, that's all about ionization energy. We have done a lot of questions and concept is also clear, I think. If you have any queries, please re-watch that particular portion. It will be clear to you. Okay, or else you can reach out to me. I'm ready to help. Now you'll be getting an assignment again from sizes, ionic radii, atomic sizes, and ionization energy. Please try it out. Okay. All right. Thank you.